This is the beginning of the third part of this presentation on Verilog, and we'll start by reviewing an overview of control and data path organization. So it turns out that virtually every digital system can be partitioned into what we would call control and data path. And the data path part is what actually transforms the data. So if you want to do some operation on data, that's part of the data path. For example, in a processor, that would be the ALU would be part of the data path. And then the other part is a control part that controls that data path and directs it on how to behave under different conditions. It also can do data steering. It can basically steer the data where it needs to go to utilize different resources in the data path. In a processor, that would be the actual controller, which houses the instruction decoding mechanism. So based on the instruction, then it tells the data path how the data flows and what happens to it. In this case, the contents of registers, memory, and so forth. So this overall abstraction is useful to have, and also keeping in mind that normally the controller is going to be implemented as some type of state machine, whether it is with hardwired state transitions or microcoded state transitions. It is a large state machine. It could also be hierarchical state machines in which states in a top level state machine are really super states that encompass a lower level state machine with its own set of states. So this abstraction is useful to understand. So as I said, we're going to see just an example of control and data path implementation. Now, if we wanted to break down, as an example, a processor, we could have these blocks, and as I mentioned, we could have that data processing block, data path, in this case, what is operating the hardware that is processing the data, and this data block here could be data memory. So we have read-write interfacing into it, and then we have this control processing block, which tells the data path how to behave. Part of that is also steering the data through the data path. And that control block could be getting the inputs from this control inputs block over here, which could be code memory, could be program memory. In fact, in processors, the actual memory interface that is right next to the processor, in this case it would be level 1 cache, is split between program cache and data cache. So you use two different buses because it's more efficient. Now it's more expensive and more complex, but you have twice the bandwidth because you have to separate independent buses. So while you are getting these control inputs, you could be at the same time communicating with the data or accessing the data. So that's what's called a hybrid memory organization versus an organization where you will share the same bus between program and memory, but that would cause a bottleneck because you can only access data or program at the same time, at a time. That's called a von Neumann organization of the memory. So you can see how this could describe a processor. So the processor, the control block is telling the data path what to do, and also observing the consequences of the results as a status and putting that out for the user. So that's a high-level abstraction of control and data path organization. And what we wanted to do here was to give you an example that is going to use a finite state machine as the controller. And we wanted to remind you that there are two classes of finite state machines, Moore machines and Mealy machines. The Moore finite state machine, the main difference between that one and the Mealy is that for the Moore finite state machine, the outputs depend only on the state. So we have the state vector here, which is really a register and the only clocked element. And we have combinational logic that, given the state, produces the outputs. You should remember this from ENG 312. And then we have the next state logic, which is again combinational logic that, given the inputs and the present state, produces the next state. So that's the Moore finite state machine. So the outputs, since they are dependent only on the state, they change synchronously with the clock. Only when the state change, which only changes with the clock, that's when the outputs change, because they only change when the state changes. So it synchronizes the outputs. And that's nice. And you should always try to use this type in this course. There is no reason to use the Mealy finite state machine, which is the only difference is that the outputs not only depend on the present vector, the present state vector, but also on the inputs. But the inputs are asynchronous to the clock. The inputs can change at any time, so the outputs can change at any time. So this gives you faster response or less latency for an output to respond to an input, and sometimes you may need that versus going through the next state logic and changing the state and then changing the output. So this could have, let's say, an instantaneous impact on the output, while the Moore, where you have to go through the next state logic and to the state vector, you will always have a one cycle, or at most, from a timing perspective, at most one clock cycle of latency or delay for the outputs to change in response to an input. And that may not be acceptable in some applications. So you have to use a Mealy state machine. For what we're doing here, you're going to do a Moore state machine, because you don't have to deal with the asynchronicity of the inputs affecting the outputs. So that's just a review, quick review of state machines. And with that behind us, I want to present a real world implementation example in Verilog, which is part of a digital it's part of an analog to digital converter that uses a sigma delta approach. And in the context of that architecture for an analog to digital converter, there is a part called a decimation filter, which is a digital filter. And this is a very important part of the converter. And we're not going to get bogged down on the theory of sigma delta modulation or how it shapes the noise spectrum and all that. I just want to give you some context, okay? And then point out how if you were designing this digital filter, which is just a part of it, everything that is around it, which is part of this analog to digital converter, even though it's not digital, could be modeled behaviorally as part of your test bench to test your, one piece of digital logic, which is this decimation filter. So that's just for context. I'm going to give you kind of a top-down presentation of what it is. So let's say you have a 2-channel sigma delta analog to digital converter. Okay, so you can see the pins of the chip here. It's got a bunch of analog stuff in the front, which are programmable gain amplifiers. It has a bunch of integrators and comparators, and together the programmable gain amplifiers, which you can program for 1, 2, 8, and 16 gain of the analog input, together with the integrators and comparators, they form what is called a second order sigma delta modulator. So here you have differential analog signaling coming into here, and now here you get a digital output. It's a high speed 1-bit digital output. Okay? In other words, this modulator implements what is called a 1-bit analog to digital converter, but it's high speed. Is much higher of the bandwidth that you are interested for this as a product. Then you put this low pass digital filter, which is the decimation filter, and you implement some function, for example, the sync cube function, and the sync function is sine of x over x. In the limit, that function has a value of 1 at 0 or DC in the frequency domain, and then that sinusoidal response in the frequency domain dies out in a 1 over x fashion, and it gets to 0 at infinity in the limit. That is the frequency response of the sync function. So to make it more prominent, we cube that and raise it to the third power. So this is a decimation digital filter that implements the transfer function cubic sync. So here we have high speed 1-bit digital input, and here we're going to get, after this digital filter, which is going to decimate the high 1-bit digital stream, when it gets decimated by this low pass filter, we get the number of bits that we want from the overall analog to digital conversion, noise free, but at a lower speed that is in the bandwidth of interest of this as a product, the analog to digital converter. So we're going to design this. But the point here and the context is that you could model all of this behaviorally in Verilog just to have a test bench to test your digital filter. This is a block diagram of the second order sigma delta modulator. So essentially, behaviorally, as you convert from analog to this 1-bit digital output, you have amplifiers and summers, and these are one clock delay as you start getting into from the analog into the digital domain. And here you have a slicer, and here you have this output. What you get is this high speed 1-bit output serial from the analog that is coming in here. The information from analog to digital is encoded in that high speed 1-bit stream, and the decimation filter converges to the number of bits that you need as a digital word. Again, this is more detail on the second order sigma delta modulator. You can see a bunch of switch capacitor filters, and which if you're on electrical, you'll learn about this in electronics too, which I teach. I love that course. So again, you could model this behaviorally. You cannot synthesize it because what you can synthesize is actual logic. But if you needed this to be part of your test bench, you could model it behaviorally in Verilog. Now let's look at the actual block diagram of the decimation digital filter. All this block diagram is digital hardware. So we have a clock. We have a clock which is the sampling frequency at which we are sampling the analog signal that we're going to convert. So that's the rate that these registers operate at. These are registers. So here you have the D input, the clock, and the Q outputs of this register, which are flip-flops, essentially. Here we have actual digital adders. These are digital adders. Then here we have another part with registers again. And here we have digital subtractors. These registers, the rate at which they are processing the data, so these are digital signal processing rates, is the sampling frequency, which is much higher than this output rate, divided by what is called an oversample rate. So the frequency of this output, of updating this, is much lower than the sampling frequency by some factor. This is an integer greater than 1. Okay? So we say that in this approach of sigma delta analog to digital conversion is an oversampling, it's an oversample system, because we are oversampling. This frequency is higher than this one, which is this one. And this is the one that where your output is coming through at, so this is a useful rate at which you can use the conversion. So the data that is coming here is at this rate. But here we have a retiming circuit that we are taking only this output every so often, as dictated by this lower frequency, Fs divided by the oversample rate. So if the oversample rate is 3, we're taking every third output from here. Now the other ones are useful because they're going back, they're being fed back. It's not like we're discarding anything, they're being fed back. But if OSR is 3, we're taking every third output. But this is our actual digital system that we're going to implement. So to summarize, we're implementing the cubic sync function. Now there is, without going into the theory, there is an equation that says that if I want this many bits, okay, of noise-free accuracy, for example, I want 16 bits, okay, I want 16 bits to convert my analog voltage into a 16-bit word. This relationship applies. The number of bits in terms of the oversample rate that I need to get those many bits. And if you solve for OSR, you get that to, you find that if OSR is 32, meaning that you have to oversample your analog signal at 32 times faster than your bandwidth of interest, then you get 17 bits of noise-free accuracy. But we're just going to set it for 16. If we can get 17, we can get 16. So that's important to know. Then we can write the transfer functions of the first part, okay? So this should remind you your signals and systems. So we can write a transfer function, discrete, in the Z domain. That transfer function is the transfer function for the top part of my block diagram. And I can also then write the difference equation. Then the second one is this one. And I can have my difference equation. There is also a retiming that takes, this is the output of the top part, which becomes the input of the bottom part, but every 32nd of it. Every 32nd Y is going to go into X as an input. So every 32nd output of the top is going to go as an input at the bottom part. So we're going to implement all of that. The first part is that I have to come up with an algorithm. Now, don't confuse the signal processing, sample, and the bandwidth requirements and the sampling rate from a signal processing or a digital signal processing perspective, which is the oversample rate times the bandwidth frequency or the output frequency, with the actual clock to implement my digital system. That is just an independent clock that needs to be as high as it needs to be for me to implement my algorithm and provide the outputs that are consistent with the requirements. So I can come up with an algorithm step by step to implement these relationships here. And that gives me the control from a state level control view of what I need to have. So I can say, well, I'm going to, at reset, I'm going to go into some state, let's say 0, 1, I'm going to leave it there to do reset stuff. But then when my output comes, on every x of n, I'm going to store x of n in an accumulator. And I'm going to start a counter because when that counter gets to 32, I need to do this part as well. Otherwise, I'm just going to stay here. Then I'm going to accumulate 2 times this quantity. So I'm holding in registers the quantities, the outputs from the previous clock cycle, from 2 previous clock cycles ago, and from 3 clock cycles ago. So I'm going to accumulate, and accumulating means adding to the accumulator 2 times this quantity. Then I'm going to accumulate that quantity again. So you can see that by doing these 2 steps, state 3 and 4, I have this term here. I have this term 3 times. I'm sorry, this one. 3 times y1 of n minus 1. Then I'm going to accumulate the ones complement of 2 times this quantity. I'm going to accumulate again the ones complement of that quantity, and I'm going to add 2. By doing the ones complement twice and adding 2, essentially I have taken the 2's complement of this and the 2's complement of this. Therefore, I have this term, -3 times this quantity. Then I'm going to accumulate this quantity, which is this one. At that point, I have the whole thing. And I update the registers. And I wait for the next X to come in. And I do the same thing. So basically, I keep on producing my X of N at the top. But every 30-second instance of the input, I'm going to make this Y the X1 here for the bottom part, the one that runs slower, to implement this relationship, the second one. So I'm going to accumulate the ones complement of this quantity, and then accumulate the ones complement of this one. And I have, at that point, I have part of this. It's not until we add 1 for each case that we have the full negative. We still don't have that quite yet, but I'm saving that because I want to do all the negative stuff together when I take care of this negative as well. Then I'm going to accumulate 2 X1 from 2 clock cycles ago, and accumulate that again. So at that point, I have this term, +3 times X1 n minus 2. Then I'm going to accumulate the ones complement of X1 n minus 3. That's that one. And then I add 3. So that adding of the 3 takes care of the 2's complement for these 2 additions that I did, and this one, making them the effect negative. And I store it, and I update the registers. So that's my control. That's an explanation, state by state, from a state machine perspective, of what I have to do. Then I ask myself, if I need to exert this control from a logic perspective, what resources do I need in my data path? So just examining my algorithm and my state sequence tells me the following. My data path, my resources that are going to change the data or process the data to get this done are, well, is a data path that is 16 bits wide, because that's what I want to get eventually. I need another accumulator, which is essentially an adder with a register at the output. I need some logic to produce the ones complement. That's just a series of inverters, because I'm doing that. I need to multiply times 2. Well, I need basically to shift by 1 left. That's a multiplication by 2. That's why I don't have a multiplier to do times 3, because it's easier to multiply times 2 and add the quantity to get times 3. That's less expensive than having an actual multiplier to multiply times 3. And I don't need the speed, because in this instance, I can have a very fast clock to do my actual state machine and data path operations. Then I need a set of registers to store the previous values of Y1 and the previous values of X1. And I need to generate the constants 2 and 3, because I use 2 here and I use 3 over here. That's my data path. Those are my resources. So when I put that together and I understand the sequence and the data flow as specified by my state sequence, I can put together a block diagram. So this is my accumulator. This is my adder. Then I have the set of registers to store previous values of y1, and also this register to store previous values of x1. And to do that, all I have to do is shift them, and they will basically act as a FIFO. Then I have my controller here, but before I determine what are the inputs and outputs of my controller, I develop the data path some more. So I know that all these different quantities are going to be operated on, so they need to be inputs into the overall data path, and I'm going to manipulate them according to the state and my state sequence. So I need a block that is going to do the shifting, or if the shifting is not necessary for the specific piece of data that is going through this multiplexer, I'm just going to pass it along. And this one is going to generate the ones complement, is going to generate the constants 2 or 3, or pass that input if none of those 3 operations apply, depending on the state. And that's where the addition happens here, and it's an accumulation, so it happens always with the present value of the accumulator gets added with what's coming down here. So I need control generated by the controller to, given the state, do data steering, which is the one out of these 6 that is going to go through here. So I'm going to call that a select one input into the data path, but an output from the controller, because the controller controls the data path. Same here. This is going to have another select that selects between these 2 operations, and another select that selects between these 4. Now the accumulator needs to be able to be initialized. It's going to be initialized either with the input x, or when I'm doing the second part, is going to be this y1 of m minus 1, which comes through here. Or if I'm just accumulating, the output of the adder goes into the accumulator as an addition. So I need another select line to control that. I'm going to call that S4, and that's another output from the controller. Other outputs from the controller is the update the registers Y for the Y stream. So here, signals to update the registers. So these registers are enabled registers, which you have a clock going, but you're not updating or letting that clock take effect unless you do want to update the registers. So you assert this signal. And when you want to update the X registers, you assert this signal. Another output of the controller is to let the external entity that is receiving the output of this is the output of the actual analog to digital converter from the accumulator after you finish the process, is a signal to tell whatever other entity is receiving that output that the output is ready. And you also take an input just to know that the input is ready as well from whatever is providing that input. The second order modulators could have a signal that says, yes, start the process. So that's an input to the controller. So the controller can start in that sequence from the beginning. So I have an architectural view. Before I do any coding, I have spent time thinking about it and specifying things before I write a single line of Verilog. The next lab that you're going to get is going to be much harder than the one you're working on. It's a processor, you won't be able to find it online or anything. It's made by me. So you're going to want to follow this process, otherwise you're going to spend a lot of time on it. So that's why this is so useful. And when you get the slides, study them. You can actually enter the Verilog in Vivado and actually simulate it and play with this design, because I'm giving you the code. But get intimately familiar and get very efficient at following this process of thinking about the problem, understanding what is needed, specifying it, and then the implementation flows very easily because you know exactly what you're going to do. You're not ad-libbing, you're not brainstorming while you're writing code. When you write code, you should know exactly what you're going to do. It should be just the mechanical aspect of basically extracting it from your brain and putting it on the screen. It should not be the time to be thinking about anything. The time to think is this one, when you conceptualize the solution. So I'm at that point. So now I'm going to have a controller, I'm going to have a data path. So I'm actually now ready to start coding. And I'm going to code the data path. So I know the data path is going to have a clock and a reset, like any system with flip-flops. It's going to have that X input. It's going to have the update register signals, the selects, and the output. The clock reset, the input, we did say that it was 1 bit. The update registers and the S2 are only 1 bit, but S3 and S4 are 2 bits, and S1 is 3 bits. And the output is 16 bits. We did specify that. So now I have my ports, and I can start doing the actual functionality. So I'm going to declare these 6 registers, which are 16 bits, plus the accumulator. This is going to become useful to define a parameter called my 0, a 16-bit 0. And parameter in Verilog, that's equivalent to what you use a pound define in C or C++. This is just a convenience, okay? So I don't have to be writing all these zeros all the time. I just have my 0. Then I have some temporary nodes, which I have because I'm going to be operating inside, and always these temporary nodes cannot be wires. They have to be regs. So these are convenience implementation things that I need to provide. And then I'm going to assign the output to the accumulator because they are the same thing. And then I start the process. It's a clock process, so, and it's synchronous. It only runs on clock or reset. At reset, in this case, my reset is 1. I'm just going to initialize all the registers to 0, as well as the accumulator. Then I just look at every possible case of the control signals when the clock is asserted. So if I'm going to update the registers, the white registers, meaning that that signal is 1, then I'm doing the shifting right here. N-3 gets N-2, N-2 gets N-1, and N-1 gets the accumulator. That's the shifting of the white registers. If I'm updating the X registers, then n-3 gets n-2, n-2 gets n-1, n-1 gets the accumulator. Cases for the select signals. So this is S1, which was a 3-bit select signal. If 0, that intermediate node is going to get, the appropriate register according to the value of S1. This implements that mux at the top of the diagram, and then I keep going down towards the accumulator, just like I had in the block diagram. Then I go down. The second block, if you remember, was either passing the signal, I'm calling that T4, and here I have T1 coming into it, or doing the shifting by 1 bit to the left. But this is an arithmetic shifting because I'm doing math here. So I have to jump through some hoops to do an arithmetic shift, which is keeping the sign bit. So I'm going to store the most significant bit, the sign bit of this output here, into this my MSB that I define over here. Then I'm going to do the shift. Okay? Then I'm going to AND with this. And then I'm going to take this ANDing, which is essentially going to zero out or mask the most significant bit, and I'm going to OR it. So this output here, I'm going to OR it with the concatenation of the most significant bit that I saved and a string of 15 zeros. So this is concatenation here, and together they represent 16 bits. So that's my shifting, my arithmetic shifting here. Then the next block, if you recall, the next block I was doing the ones complement, so that's easy enough. That's just inverting the output of this case, which is P4, or passing, or generating the constant 2, or generating the constant 3. And then the last case, the last multiplexer was either initializing the accumulator with a 1-bit X. So basically I have 15 zeros here concatenated with a 1-bit X. So together they form 16 bits for the accumulator. The other case is that I was storing in the accumulator y1 of n-1, the output of that register. And that was to start the second process. So every 32nd time I was doing that. But the common case is this one. The accumulator is accumulating. The accumulator is equal to the accumulator plus P5, which is the output of this part here. So then I can close the always, or this n belongs to belongs to this else if here. This n belongs to the always, and the n module belongs to the end of the module. So this is my data path. I know exactly what it's doing. I can visualize it almost from my block diagram because I spent time doing it. I didn't start typing all of this. There was no way that, it would have come out to be that nice. So now I have my data path and I have an interface for it because I declared the ports. So I'm ready to start my controller, which is going to be a state machine. A Moore state machine like we discussed. So my state machine, I already know the interface of my controller because I looked at it. It was in my block diagram. And I know the sequence of states because I put down the state sequence one by one. So I know that my controller is going to have a clock and a reset. I said it will have the input, the input ready signal. And then we discussed these control signals for the data path, update Y registers, update X registers, the select lines, and the output to tell the next entity downstream that the output is valid. So we know that these are the three 1-bit inputs, and we have some 1-bit outputs, and we have same width as the data path because they're going to connect together. So I have my ports. Then I have some parameters, again as a convenience, the state numbers. And I counted 17 states from 0, actually 18 states. The outputs are being recasted as regs because, again, I'm going to use always blocks, and if they are in the left-hand side of an assignment, they need to be regs. Then I'm going to, and this is the way that you code a state machine. Just like the state machine has 3 blocks, the next state logic, the actual state vector, the actual register for the state, and then the next part is the output logic. So I'm going to declare the present state, which is actually the output of the state register, and the next state, which is the input to the state register. And since I have 18 states, then I need at least 5 bits. Then I'm also going to need a 5-bit counter because I need to count. This is not part of the state machine, but it's part of the controller. Because I just need to count. I just need a dumb counter so that it counts 0 to 31. And when it rolls over, I know that I need to take the output of the top part of the block of the algorithmic block diagram to do the bottom part. So here I have an always block that is sensitive to the present state. So you can tell that this always block is going to implement the output logic because the output logic produces the outputs depending on the present state for a Moore state machine. And I just go down the states in my definition of the state sequence, and I know, depending on what I'm doing, what signals I need to assert. In other words, what signals need to be a 1 or true to make something happen in the data path, otherwise they're 0 and the data path is not going to act upon them. So if the state is 9, that's when I update the Y registers. If the state is 17, that's when I update the X registers. If the state is 5 or 6, that's when the S1 signal is 1. And when the state is 8, the S1 signal needs to be 2, because I know what I need to pass, again, from my diagram and the state sequence that I specified. I can also tell when the state is 10 and 11, S1 needs to be 3. And when the state is 12 or 13, it needs to be 4. So when the state is also 14, that signal needs to be 5. Otherwise, it's going to be 0. It's not going to be asserted. And I do the same thing for all the different signals. This is for S2. So S2 gets asserted gets asserted, and I can control what the assertion levels are, whether I want it a 0 or I want it a 1. Okay? But I just look at the states. States 3, 5, 10, and 12. S2 is 0. Otherwise, it's 1. For S3, state 5, 6, 10, 11, and 14 is 0. For state 7 is 2. For state 15 is 3. Otherwise, it's 1. That's from looking at my state sequence. And then for signal S4, if it states 2, I know that it has to be 0. If it's 16, it has to be 1. Else it's going to be 2. And finally, if I have a state 15, that's when I complete the process. That's when I'm going to make the output available 1 to tell the other entity that the output is valid. Otherwise, it's going to be 0. And I have my output logic operating and generating all the output signals that are going to control the data path. So that's one part of the state machine. The next part of the state machine is the register, the state register itself, which is very simple. On clock or reset, if the reset, I'm going to basically reset the state and reset the counter. Otherwise, the present state becomes the next state. So basically moving the inputs of that register to the Q outputs. And then if the counter rolls over, okay, this is the counter, I'm just going to reset the counter back to 0. Otherwise, the counter is just going to count. And then finally, this is the next state logic. Again, if I look at my state sequence, I can see that when the present state, because the next state logic depends on the present state and the input, but I only have one input. Remember that the X is an input to the data path, but the controller is told to start the sequence by this input control signal from the previous, in this case, the second order sigma delta modulators block. So this is the next state logic, where I generate the next state. And if I look at my sequence, I can see that if I am, with a case statement, if the present state is 0, that is the reset, and my input is valid, it's telling me to start, I go to a state 2. If a state is 1 and I'm told to start, I go to state 2. So a state 0 becomes a hardware reset state, and a state 1 becomes a begin state without a reset. So that's why they're there. And then if I look at my state sequence, it's very sequential in nature. So if the state 2, next state is 3. If 3, the next one is 4. 4, next one is 5, and you can see and so on. Until I get to state 9. Now in state 9, if the counter is 0, then I go to state 10 and do the second part, which is given by these states. But if the counter is not 0, it hasn't rolled over, then I go to state 1 again here and start the process again if the input, when the input is valid. But if the counter rolled over, meaning that I'm at my 32nd output of the first part, then I do this part. Go to a state 10, and from state 10 to 11, from 11 to 12, and so on, until I get to stage 17, and in stage 17 I go back to stage 1. This is the next stage logic. Very easy to visualize if you went through that specification exercise. So now I have the data path and the controller. All I have to do is hook them up together because I know the interfaces. From the perspective of my filter is a digital system which is going to have a reset and a clock. It's going to have the X is valid input. It's going to have the output and another output that is going to tell the next entity that output is valid. So I have these 1-bit inputs, 1-bit output, and the 16-bit output, which is my actual conversion. So all I have to do is define some wires to hook up the controller and the data path together, and I have my filter. So hopefully this sort of real world example gives you an idea and something to use as an example to develop your future projects and labs in this course, and also gives you some insight into the methodology of specifying something before you actually implement it. And furthermore, how to partition the system between data path and controller, how to do those as when you specify beforehand, and then connecting them together to do an overall system. Okay.